Hello everyone. While dealing with the subject of digital communication, some introductory portion of digital signal processing have also to be covered. So I would like to start with that and then I will come to the actual contents of digital communication. And teaching this subject is that it's a rapidly developing technology for scientists and engineers. DSP can be applied in many areas like control and power systems, biomedical engineering, automotive engineering, telecommunications, mobile communication, radar, sonar processing, and neural computing. Now, with the advent of low cost digital signal processors, manufacturers are producing plug in DSP boards for PCs. Together, they are also using very high level tools to control these boards. The point is that with the advent of these DSP chips, this technology has really can be applied in various fields of engineering. Now let's start with the introduction to digital signal processing. Basically, this is an analog processing system where there can be two types of signals. One is analog, which is a continuous signal, and the other can be a digital signal or a discrete signal. We will come to these two types of signals once we move along the class. Now, XT is the analog input signal, which can be composed of either a speech signal or a video signal. NT is the noise added into that signal. Now, this signal goes to an analog signal processor, which is basically a low pass filter to cancel out the effect of noise present in the signal. And the output is also analog output. So input is also analog and the output is analog signal. So therefore, this is an analog processing system. But the disadvantages of this kind of system is the cost involved in the analog signal processing once we expect higher performance from the systems. The counterpart to analog processing system is the digital signal processing system. The block diagram is shown here in figure 2, which provides an alternative method for processing the analog signal. Now, if you look at the first block, xt is the analog signal taken from some transducer. It is applied to an anti-aliasing filter. Now, this filter is required here because the sampling theorem says the analog signal can be recovered from digital signal if the sampling frequency is at least twice the maximum frequency component in the analog signal. Now, to band limit the analog signal, we need to put here an anti-aliasing filter so that the maximum frequency component in the analog signal can be limited, can be band limited. So therefore, this signal basically can be band limited. It's a low pass filter basically. Now, after it passes through the anti-aliasing filter, it goes to the analog to digital converter because we have to convert it into digital domain to apply DSP tools on signal. We will discuss about these blocks in detail. So once the signal goes into the A to D converter, then it goes to the digital signal processor, which processes the signal in the discrete domain, and various algorithms can be applied here on the signal to take advantage of the DSP techniques. Now, after processing the signal in the DSP chip, the signal is then applied to a D2A converter, which is digital to analog converter, to convert it back to the analog form. Uh, D2A converter actually introduces quantization noise in the signal, and and we have to actually reconstruct the signal from the digital domain back to the analog domain. So in the end, there will be a reconstruction filter, which is an analog filter, and this will basically convert the digital signal into the analog signal. We will discuss the details of this block diagram in the coming slides. The same is written here in this slide. The A to D converter converts the analog input signal into a digital form. The D to A converter converts the signal back into the analog form. The reconstruction filter smooths out the outputs of the D to A converter and removes unwanted high frequency components. The analog filter, which is at the start, this filter basically, the analog filter is used to band limit the analog input signal prior to digitization. This filter is actually used to avoid the effect of aliasing, as stated by sampling theorem. We will also discuss aliasing in detail in the coming slides. The heart of the system is basically the digital signal processor. The example that I have taken is a TMS 320C60. Now, many more advanced versions of the DSP chips are available now in the market. So we can use those DSP chips either in the fixed point type, or we can also use the floating point type of DSP chips. The digital signal processor may implement one of the several DSP algorithms like digital filtering, or it can do some kind of analysis. It can take the FFT of the signal and analyze the frequency components in the signal present in the signal. Digital signal processor implies that the input signal must be in a digital form before it can be processed, as it is obvious from the block diagram that I have shown to you. Now let's look at the analog to digital conversion process. Before any DSP algorithm can be performed, the signal must be in a digital form, and the job is done by the A to D converter. And we also know that the signal needs to be band limited, and it is passed through the anti-aliasing filter. The process of analog to digital conversion involves the sampling and hold. Then we have to quantize the signal and then digitally code the signal. Let's look uh, this analog to digital conversion process with the help of a block diagram. Now XAT is the analog signal which is band limited after passing through the anti-aliasing filter. Now this band limited analog signal is then passed through a sample and hold circuit. Now what is a sample and hold circuit? This switch is there. This takes the sampling voltage of the, once this switch closes, it takes the voltage of the instant, of that particular instant, and charges this capacitor to that particular level. Now once this switch is open, the capacitor will not have any path to leak. So therefore, capacitor will not have any path to discharge. So therefore, the voltage will remain held at that particular voltage point. So basically, this switch is acting as a sampling, part, and this capacitor, the closing of this switch is taking the samples, and the opening of this switch is actually holding the voltage. And this opening and closing is done at sampling frequency rate, which we have denoted as Fs, right? We will we will see the process again in the diagrams. After the sampling and hold, so the sampling is done. This diagram basically shows the sampling and the holding part. We'll come to that later. So the next block in the chain is the quantizer, because once the sample is taken, uh, the sampled value will have to be quantized, meaning by, let's say I have an A to D converter of B bits. How many quantization levels will be there in the quantizer? There will be 2 to the power B quantization levels in the quantizer. That particular value of the sampled signal will be given a quantization, will be approximated to a quantization level out of these 2 to the power B quantization levels. We will see how it is done. After the signal is quantized and is allocated one level, one particular level, then that level is converted into a digital code using the encoder circuit, and we get B bits out of this block, out of the system. So the input was an analog signal, and the output will be a digital signal in terms of the bits. Now let's look further into the details of these circuits. Now this is the sampling process explained. The dotted line basically gives the analog signal. The sampling is done. This is capital T is the sampling period. After every t seconds, the sample value is taken, which is the opening and closing of the switch that I showed you here. The opening and the closing of the switch will basically take these sample values. So these are the samples taken, and this is the sampled version of the analog signal. Now, sample and hold takes a snapshot of the analog signal every t seconds and then holds that value constant for t seconds until the next snapshot is obtained. Now, if you see, this is the analog signal. So the snapshot is taken, this is the sampled value, and then it is held for capital T seconds. Then again, the next sample is taken and the value is held. So in this way, this is the sample and hold output, and the sampling frequency is Fs, which is basically the reciprocal of the sampling period. All right. Now this diagram actually explains the quantization levels. Now let us say this is just a hypothetical quantization process explained, and this says this line, this is basically the analog signal, these are the samples taken. Now this sample is nearer to 1 quantization level as 1. This whole axis is divided into levels from 0 to 6. This one is 1, 2, 3, 4 up to 6. Now this sampled value here, the dot here shows the sampled value at that particular instant. This is closer to 1. Now if it is closer to 1, it will be allocated a code of 001. Now if you take this sampled value, this is more closer to 4. So therefore it is given a code of 001, which is 4 in digital form. This is more closer to 5, so therefore this is given a code of 101. In this way, the quantization level, the quantization process quantizes the signal to a particular level, and then level is then coded into the digital form. Let's explain further into the quantization process. Now let's look at this diagram. Now this is, let's say this bold line here shows the level n minus 1. The second bold line shows the level n, and the third one shows the level n plus 1. In between the two lines is the middle line, right? If the sampled value is above this middle line, we will allocate level n plus 1. If the sampled value is lower than the middle line, we will allocate level n. And in this way, the quantization process is completed, meaning by the sampled values are given the quantization level, the allocated quantization level, depending on where the sampled value lies. Whether it is above the middle level, then n plus 1 will be allocated, and if it is below the middle level, then n level n will be allocated. Now between the two, if you look at the diagram carefully, between the two levels, what is the what we between the two levels we define it as delta V, which is the step size, which we call as the step size. The maximum now here the quantization process actually introduces quantization noise. Suppose a signal is, let's say, at the middle level, right at the middle line, and we allocate level n plus 1, but actually the sampled value actually belong to level n. So what is the quantization error? uh, uh, the range of the I mean the quantization, the maximum value of the quantization error can be delta V by 2, because the sampled value was lying here. It should have been allocated n, but we allocated n plus 1. So what is the difference between the actual sampled value and the level is delta V. Maximum difference can be delta V by 2. That's the maximum value of the quantization error. Every time the quantization process will introduce quantization noise in the signal, and quantization error maximum value can be delta V by 2, one half of an LSB basically. Now I will explain, let's say if the step size is between the two levels, the voltage is 4.9 millivolts. I will explain how we have come to this 4.9 millivolts. But let's say if the difference of the voltage between the level n plus 1 and level n is 4.9 millivolts, then the quantization error can be delta V by 2, which is 2.45 millivolts. This can be specific to specific kind of A to D converters. We'll look again into the detail later. Now this is the coding process further explained. Uh, in this diagram, we can see that how the coding is to be done. The coding, if it is a bipolar type of coding, meaning by let's say it's a 4-bit converter, there can be 16 quantization levels. Now the digital values can range from in a unipolar fashion also and in the bipolar fashion also. For the if it is in the bipolar fashion, the negative values will be represented by the 2's complement notation. For example, this is level 1. The code given to this voltage level is 0001, and the opposite to this is, let's say if it is -1, take the 2's complement of this, it will be 1111. So that means if it is a bipolar kind of A to D converter, we can use the 2's complement notation to represent the negative values. If it is a unipolar one, so it will be a all the positive values of the digital form will be there, corresponding to each quantization level. Now, for an A to D converter with binary digits, the number of quantization level is 2 to the power b. What is b here? B is the number of bits the A to D converter will output for each sampled value. Number of quantization levels will be 2 to the power b, and the interval between the levels, that is the quantization step size, which is delta V, as I have already explained. Delta V is the step size, which is the difference between the two levels. Now, what is V? V is actually the full range of the signal, full range of the quantizer that can accommodate the analog signal. V is the full range. In the next slide, probably it will be clear. V is the full range of the A to D converter, and it is divided by 2 to the power b minus 1. Approximated, this 2 to the power b minus 1 is approximated to 2 to the power b. So that will be the step size. Step size is given by the full scale range divided by the total number of quantization levels minus 1, which is v over 2 to the power b. Now, I have taken an example here. Let's look at this example to understand the process completely. Let's say I'm considering a 12-bit A to D converter. What is 12-bit here? This is capital B basically. It's a bipolar A to D converter with an input voltage range of plus minus 10 volts. Now the range of the voltage, meaning the range of the A to D converter is minus 10 is from minus 10 volt to plus 10 volt. That means the peak to peak range is 20 volts. The full range we have to take, and we'll have a least significant bit of what is the value of the least significant bit will be given by, or the step size basically, the full peak to peak range, which is 20 volt, the capital B, which is 12-bit A to D converter here. So it is 2 to the power 12 minus 1. It comes out to be 4.9 millivolts, which is also known as the resolution of the A to D converter. Now, the, this portion of the slide shows the quantization levels. Because there are 12 bits in the A to D converter, how many quantization levels will be there? 2 to the power 12 will be 4096 quantization levels will be there. And 12 we will, at the output of the A to D converter, we will get 12 bits for every sampled value. Every sampled value, after going through the process of sampling and hold, quantization and coding, will give a 12-bit output. And the resolution, as I have already explained, or the step size is 4.9 millivolts for this particular example. Now, let's let this slide basically we will try to look at what is the quantization noise actually. What is the value of the quantization noise power? Let's take the case of a sine wave. For a sine wave input of amplitude A, the amplitude of the sine wave is A. The quantization step size becomes the full range from the positive peak of the sine wave to the negative peak. It is 2A. How many bits will be required to code the sample? Let's say it is B bits. So therefore, what is the step size? This is the 2A is the full peak to peak range, full range of the A to D converter, and divided by the total number of quantization levels, which are 2 to the power B. Minus 1 was there, but we have approximated it to 2 to the power B minus 1 is approximated to 2 to the power B only. So 2A is the full range of the analog signal, uh, which which fully accommodates the analog signal. Now the quantization error, let's denote it by E, for each sample is normally assumed to be random and uniformly distributed in the interval plus minus delta V by 2. As I have already explained, the maximum value of the quantization error can be delta V by 2. So either it can be on the plus side or it can be on the minus side. So that's why this plus minus is there with zero mean, of course. In this case, the quantization noise power or variance. Let's try to look at the quantization noise power and try to derive it. E is the actual amplitude minus the quantized amplitude. Actual amplitude of the sampled signal minus the quantization, minus the value of the amplitude which is given to that particular sample value based on the quantization process. Let's try to derive the case. Now sigma E square is the variance, right? And the variance is given by E square, which is the quantization noise, into the probability density function, and taking the integral of this, the limits are from minus delta V by 2 to delta V. I have taken to delta V by 2. I have taken a general case of the uniform distribution of a random variable. Now, let's say there is a random, the PDF of a random variable is given by, if it is constant, if it is from, let's say, because if it is uniform, the the initial value is A, the final value is B, right? And this probability density function is given by 1 over B minus A. Now in this case, in our case, what is the range of the quantization error? It can be delta V. Delta V is the full range or full range between the two quantization levels. So that's why if it is from, in a general case, if it is from B to A, the probability density function is given by 1 over B minus A. But in our case of the quantizer, the range between two quantization levels, the value of the voltage between the two quantization levels is denoted by delta V. So since it is 1 over B minus A, we will take here the probability density, we will equate the probability density function to 1 over delta V. Right, so that's why this PE is actually replaced with 1 over delta V and limits remain the same. Now if you solve this integral, right, this integral will give you the variance of the quantization noise, and actually it is delta V square by 12. The caveat is that the we are taking the case of a uniform quantization. That means the step size is same for all the quantization levels. That's what is explained here. Uniform quantization means all steps are of equal size. There is a possibility that we can increase, we can have different step sizes also, but for the initial case and for the explanation purpose, I am taking a uniform quantizer, meaning by that all these steps are of equal size. And the quantization noise, which is basically the noise, which is basically the variance, is delta V square by 12. Now let's try to, this is a very important actually result that we will obtain from here. For the sine wave input, uh, the average signal power is a square by 2 because the RMS value is the amplitude divided by the root 2, and we have to square it to take the power. So the average signal power is a square by 2, and the quantization noise power we have already calculated, which is delta V square by 12. Now let's try to see what is the signal to quantization noise power ratio in decibels. Now SQNR is 10 log because it's the case of powers. So that's why this 10 is here. 10 log the input power, which is the signal power a square by 2, the output power or the noise power. So this is delta V square by 12. We have already derived and calculated these. If you solve this, what you will see is SQNR is given by, if you just do some manipulations, you will see that SQNR is given by 6.02 into number of bits plus 1.76 dB. You can derive this formula if you do some mathematical manipulation. Now, this is a very important result actually. The SQNR increases with the number of bits. Now, if an A to D converter is, let's say, a 10-bit A to D converter, meaning by for every sampled value, it gives an output of 10 bits. And then if we use an A to D converter of 11 bits, there is an improvement in the SQNR, right? And if you see this table, this is for the first row explains the number of bits, levels, and SQNR. If the number of bits of the A to D converter are 3, how many levels will be there? 2 to the power 3 will be 8. And what is the SQNR? Calculated using this formula is 18.7 dB. Now, if we increase now the number of bits by 1, let's say, 4 bits are there. How many levels will be there? 2 to the power 6, 2 to the power 4 will be 16. And the SQNR is 25.3. There is a difference of approximately 6 dB. Now, if you see the number of bits as 5, increased by 1 from 4. The number of levels are 2 to the power 32, 2 to the power 5. The number of levels will be 32. What is the SQNR? 31.6. Again, there is a difference of 6 dB from a 4-bit A to D converter to a 5-bit A to D converter. And if you look at all the variations of the number of bits in the A to D converter, you will see that the with every increase in 1 bit of the A to D converter, there is approximately a 6 dB gain in the SQNR. But the problem is that if you increase the number of bits, if you increase the number of bits of the A to D converter, then the cost of the A to D converter will increase. So you have to make a trade-off, basically, where how many bits you require to convert an analog signal to the digital form. There must be a trade-off worked out to see how many bit A to D converter is required, and of course the cost. Thus, the signal to quantization noise ratio increases approximately 6 dB for each bit. This is a very important result of what we have driven. So basically what we have, let's look at the summary. What we have done till now, we have tried to look at the analog to digital conversion process. We have an analog signal which is xt, it's in the time domain, and a continuous signal basically. Let's say the range of this signal is 0 to 5 volts, right? The maximum range of the signal is, let's say, 0 to 5 volts. If it is applied to a 12-bit A to D converter, unipolar and bipolar I have already explained. You need not to take the 2's complement of the rest of the half portion of the levels. So you will take all the positive values in the digital form. So with every sample, because in the A to D converter will be sample and hold, quantization and coding. 3 blocks will be there in this one block shown here. I have already explained. So after it goes through all those 3 blocks, the output will be a 12-bit digital form, coded form, right? Now, an analog signal is in the continuous domain is represented as xt, and in the discrete domain it is represented as xn. I will explain once we start the theoretical concepts of the DSP. I will this thing will be clear, what is xn and what is xt. Now for this particular example, what is the step size? Because the range is from 0 to 5 volts, 5 volts divided by, since it is a 12-bit A to D converter, 2 to the power 12 minus 1. So that will be the step size or the resolution of the analog to digital converter. Now there is one more specification of analog to digital converter, which is the conversion time. Say the conversion time of this A to D converter is 35 microseconds. Now what is the importance of this A to D? What is the importance of conversion time? The meaning of the conversion time is that the moment you apply the analog signal to this A to D converter, in how much time it gives the digital output. That is the conversion time. Say here in this case it is 35 microseconds. All right, that actually describes the speed with which the analog to digital converter converts the analog signal to the digital form. Now, in practice, the A to D converter is preceded by a sample and hold circuit, which we have already seen, which freezes the signal during conversion. We know that the this is the block diagram. This is the simple diagram of a sample and hold circuit. This in this switch, this position is the sample position, and once the switch opens, it is the hold position, and this is the capacitor. I have already explained. There are 2-3 important parameters which we need to look at for a sample and hold circuit. Now let me have the presenter's view here actually. So if you look at the now, there are two important specifications of a sample and hold circuit. One is the aperture time. The second is the acquisition time. Now, this is the start. This is how the input. This is how the input voltage will start rising. Now, what is acquisition time? The time required for the charge in the holding capacitor to rise up to a level that is close to the input voltage. So, because the capacitor will start charging, ultimately it will go on and reach to a particular level very near to the input. So, this time is actually the acquisition time. It depends on the RC time constant of the circuit. The slew rate, if you're using an op amp also, I have not taken that active circuit here, but that will also depend on the, if you modify the circuit, there will be an operational amplifier, and that will also depend on the slew rate of the operational amplifier and so on. So that means this is the acquisition time. The second important specification is the aperture time. What is the aperture time? The time delay between the initiation of the VO track. Now, here the output starts, at this point, the output starts tracking the input voltage. Still now the hold has not come into action. It's only sampling taking place. Time delay between the initiation of the VO tracking the VI and the initiation of the hold command. Now this timing from this point to this point is the aperture time, when actually the output voltage of the sample and hold circuit starts tracking the input voltage. This is aperture time. Now, uh, now after that it will, the value will be held because the hold action will come into play. And there is one important point to be noted is the droop in this signal. Now, what is droop in this signal? Voltage droop is a phenomenon where the voltage across the holding capacitor drops down due to, because there will be some leakage current. The capacitor will not be an ideal capacitor, so there will be some leakage. Due to that leakage, the voltage will start decreasing, will go away from the actual tracking of the input signal, and that is known as the droop. Actually, these droops in the signal have to be minimized. That will depend on the quality of the sample and hold circuit used. But let's concentrate on our requirement. Two parameters related to sample and hold circuit are there: aperture time. For example, let's say it is 25 nanoseconds. The acquisition time is 2 microseconds. Now, what I am trying to calculate, because the sample and holds, you cannot choose any sampling frequency. You have to, depending on the operations and the functioning of the sample and hold circuit, you actually will have to decide the sampling frequency, the opening and closing of the switch and the holding action, because there are some limitations of the physical components. So the maximum sampling frequency that can be converted for that can be used for the conversion is given by 1 over 35 is the conversion time, plus 2 plus 0.025 this nanosecond. So that means this example that I have taken will have a maximum sampling frequency of 27 kilohertz. Maximum sampling frequency for the above A to D converter can be 27 kilo. This is just an example that I have taken, but will fairly give you an idea of how the analog to digital conversion process takes place, how the sampling is done, how the quantization is done, how the coding is done, and how you can choose an A to D converter, how many bits you will choose for the A to D converter, because number of bits actually give you a high resolution but will increase the cost, and how you have to select the sampling frequency of the A to D converter. So these are some basic specifications of an A to D converter. Now let's go further. Now this slide explains, let me come out of the presenter's view, hide presenter view. Okay. Sampling of the analog signal. As I have already told you, this xt is in the continuous domain, xn is in the discrete domain. This x of big omega actually gives the Fourier transform in the continuous domain. These will be very important points because we are directly entering into the real digital signal processing theory part. And this x omega, small omega, is the Fourier transform of xn. Now, one very important um, point that I want to stress here is that this big omega is the analog frequency. Please remember throughout this course, this big omega is the analog frequency. This small omega is the digital frequency. I will explain what is the difference between an analog frequency and what is the difference between a digital frequency, between the analog and the digital frequency. But you must keep in mind, repeatedly I am saying that big omega is the analog frequency, small omega is the digital frequency. All right. Now, the A to D converter will sample the signal at sampling frequency is denoted by Fs, and which is also given by 1 over T, where capital T is the sampling period. All right. Now, how the sampling is done, how you can mathematically explain the taking the discrete signal from the analog signal. Let's say xt is the analog signal. For every t value, this variable t, you replace it with the small n and capital T. Small n is the sample value and capital T is the sampling period. We will take examples also. Now, we will also see that this digital frequency is actually given by the analog frequency into capital T. All right. Now, this big omega, which is analog frequency, is 2 pi Fa. Fa is the analog frequency of the analog signal. What is capital T? We can also say capital T is 1 over Fs. This is a very important result. The digital frequency is equal to 2 pi analog frequency of the signal divided by the sampling frequency. Very important point which will be used in throughout your DSP course. Please remember, once again I am repeating, this small omega is the digital frequency, capital omega is the analog frequency. It is 2 pi Fa. Fa is the analog frequency divided by the sampling frequency of the A to D converter. This is how the sampling of an analog signal can be explained mathematically. Now, this equation gives you the inverse Fourier transform formula in the analog domain. X omega, x of capital omega is the Fourier transform. Now, this is the regular formula used. Now, how you can convert xt is the analog signal obtained from this x omega, capital omega. Now, how you can convert this signal into discrete domain? Very important, you have to replace small t with n of n and capital T, like this. Now, if you do this, this t is replaced with x of nt equal to 1 of the same integral, x of big omega e to the power, and we replace this small t here with n of capital T. Or we can also, for simplicity purpose, we can remove this capital T from here, but actually it is there. Actually, it is there, but for simplicity, we will not write capital T. We will say it is Xn. So Xn is the signal in the discrete domain, and this is the formula of getting a signal in discrete form from a continuous form. Now, x of nt, which is the discrete form of the signal, is 1 over 2 pi integral going from minus infinity to infinity. This is the analog spectrum, e to the e of j big omega n capital T, right? Now, basically, this has been obtained. This is the same equation as we were discussing in the previous slide. The same equation I have written here. Now, this factor e to the power j big omega n capital T is the phase factor. It is a basically it is a periodic function of 2 pi. The spectrum, that means this analog spectrum will repeat after every 2 pi for this digital in the digital domain. Now, equation 1 will, because the integral is going from minus infinity to infinity, and this factor is periodic function of 2 pi, so I can do a little modification here. I can use an index k. The index k goes from minus infinity to plus infinity, and the integral limits can be changed from 2k pi minus pi to 2k pi plus pi, because a limit from 2k pi minus pi to 2k pi plus pi will give me a period of 2 pi. Rest of the things remain the same, and I also divide this whole equation by capital T and multiply it with capital T. Now, doing for I mean, because it's a I can, because these limits are for this omega variable, so I change this omega variable into omega big omega plus k of 2 pi by t, and same here for omega variable, and the limits now of the integral will be minus pi to pi. All this manipulation I have been able to do because the signal, because this factor is a periodic function of 2 pi. Now, doing going further in doing the manipulations, I can take the sigma inside the integral and integral outside, so the rest of the equation remains the same. Now, I know that small omega, which is the digital frequency, is equal to big omega, which is the analog frequency, and sampling period, right? I can replace this the big omega and capital T with small omega. And after doing this, my x of n will be 1 over 2 pi. And this uh, capital omega, capital T, big omega and capital T is replaced with small omega. All right. Now, this is the modification done in this equation. Now, we also know that the inverse Fourier transform in the discrete domain is given by xn is 1 over 2 pi integral going from minus infinity to infinity x of small omega e to the power j small omega n, right? Now, comparing equation number 2 and equation number 3, I can say that this x of omega, capital X of small omega, which is the digital spectrum basically, is equal to this 1 over t sigma x, and this term capital X of big omega plus k of 2 pi by t. Now, the same I have written here. That means x of small omega is 1 over t sigma going from k sigma gain going from this k going from minus infinity plus infinity, and x of big omega plus k over 2 pi k of k into 2 pi by t. Now, this basically is the digital spectrum. This forms the analog spectrum, and this factor says that this is repeating after every 2 pi period. All right. To the diagram, let's look at this. Now, this diagram tells me this is the analog spectrum, right? The x-axis has big omega, which is the analog frequency. The y-axis has the amplitude, and x of capital omega is the spectrum in the continuous domain. Now, if the value, please remember also, capital omega is equal to pi by capital T is actually Fs by 2. You can calculate this. You can use the formula capital omega is 2 pi f a. Fa is the sampling frequency. Now, what I mean to say basically here is that if the analog spectrum, because we have the analog signal and we have to convert it into digital form. The point is that if we take the Fourier transform and if the analog spectrum of the analog signal is defined by this case 1, where x omega is the analog spectrum, is 0, outside this minus p by t and plus p by t range, if it is 0 outside, this is the analog spectrum, and we are getting these results from this formula only. And if this is the analog spectrum and we do the analog to digital conversion, now in the digital domain, x-axis will be small omega, which is the digital frequency. This is the digital spectrum, because this x of omega, this expression, equation 4, actually relates the digital spectrum with the analog spectrum. Now, if this is the analog spectrum and the analog signal is 0 outside this range, the digital spectrum will repeat the digital, this minus pi by t in analog domain is actually minus pi in the digital domain, plus pi by capital T in the analog domain is actually pi in the digital domain. So we get the same spectrum, but this spectrum will repeat after 2 pi. It will repeat from minus infinity to infinity. So basically this signal from the analog spectrum will become a replica in the digital domain from minus pi to pi, right? And it will repeat after 2 pi further. So this is the digital spectrum and this is the analog spectrum after we have done the analog to digital conversion process. Now let's take the second case. This is omega, big omega equal to pi by t. This is the derivation explanation I have given to you. Actually, big omega equal to pi by capital T corresponds to small omega equal to pi, or f is equal to fs by 2. Very easy to derive. Take big omega as 2 pi fa, and digital frequency as 2 pi fa divided by fs, or take small omega equal to big omega into capital T. The digital, this is an important result. The digital spectrum is the same as the original analog spectrum and repeats at multiples of the sampling frequency. Very important result. Now, let's take the second case where analog spectrum is not 0 beyond this minus pi by t and plus pi by t. This part of the diagram shows that, figure 8 shows that the x capital omega is not 0 outside minus pi by t to pi by t. So that means the signal, the analog spectrum extends beyond minus pi by t to pi by t. And once you do the analog to digital conversion process on this signal, since the now up till here up till here, the digital signal will repeat from minus pi to pi, right? So it goes from here to minus pi. It goes, um, in this case, the overlapping of the signals will take place. Overlapping of the signal, because this analog signal is extending beyond minus pi by t and pi by capital T. Because the digital spectrum has to repeat. Now the repetitive portion of the spectra will overlap with the consecutive replicas. So therefore, this is known as aliasing. Frequency response of an analog signal whose IS frequency component is larger than the sampling frequency. Now this below diagram, frequency response of the sampled analog, the overlapped region represents aliasing. Now, if the sampling frequency Fs is not sufficiently high, the spectrum centered on Fs will fold over or alias into the baseband frequencies as shown in the figure 8. Because if the spectrum extends beyond minus pi by t and on the negative side and beyond pi by t on the positive sides, so there will be overlapping as shown in this figure. Okay. Then that's what is said here in this equation. The analog spectrum should be equal to 0 with modulus of omega greater than pi by t. That means beyond minus pi by t and beyond on the negative side and beyond pi by t on the positive side. This results in familiar sampling theorem. The minimum sampling frequency for which equation 4 holds is called Nyquist frequency. Now I have completed with the A to D conversion part. In the next lecture, I will cover digital to analog conversion. Thank you.